This question, the difficulties people had with it seemed largely to be about algebra. So let's look at it a little more closely together. We have our spring attached to M. We're told it's a frictionless surface, spring constant K. So no matter what happens, the spring constant is going to be K. It's oscillating with period TP when it's block P, amplitude AP, from its equilibrium position, XO. Now this is an odd reworking of what this XO actually means. XO usually means the maximum amplitude. In this case, this is the equilibrium spot, and we would then oscillate out here to amplitude P and an equal amount in the other direction minus amplitude P. So we have this block going back and forth undergoing simple harmonic motion. We know that when it's out here, the spring is stretched the fullest. So that is when it has the greatest potential energy and the velocity is 0. When it reaches here, all that potential energy has been converted to kinetic energy. So this is where it's the fastest, has all the kinetic energy, and this is all the potential energy out here. And so we have this interconversion between the kinetic and potential, and that total remains the same, such that the kinetic energy here at the equilibrium point equals the potential energy at AP and at minus AP. So we understand what's going on with that now. A second block, mass Q with a mass 2m, is dropped, and however you want to think about it sticking, it sticks. It sticks to this block. Maybe there's Velcro, something like that, and immediately sticks. At the instant it passes through the equilibrium position, so when it's at this location, the equilibrium position, we drop that block, it sticks at that spot. Sticks at that spot. So what we now have is a collision, and we have the momentum being conserved. So the momentum being conserved, we know P0 equals P. And beforehand, we have MV, and it's just MV. And afterward, we have these two stuck together particles. It's 2m plus m times a new v, v prime. And this, of course, is an elastic collision. Excuse me, an inelastic collision. That means the kinetic energy is not conserved. For momentum to be conserved, this momentum that was present in block P with mass m is now being shared with them. So the velocity must decrease. The velocity is going to decrease, which means the kinetic energy is going to decrease. And if the kinetic energy decreases, then this kinetic energy, since it's less, will not go as far in either direction. And the two-block system, and there's a period for these two situations. There's a period when it's P, and there's a period when it's P and Q. So how do they compare with each other? The possibilities, if we were just mapping them out, logically are, it could be equal, they could be equal to each other, so it's 1. It could be greater than 1, or it could be less than 1. The ratio of these two things, TPQ to TP, would be greater than 1 if TPQ is greater. And it would be less than 1 if TPQ is less, or TP is larger. So the question is, what is happening? The first step we have to take is to find that relationship. And the relationship, just from the outset, when we look it up on the formula book, the period of a spring, or something undergoing simple harmonic motion, is 2 pi times the square root of m over k. Well, that means we have two expressions. We have one for TPQ, which is 2 pi times the square root of PQ, it's 3m. Because when it's PQ, there's a total mass of 3m. And the spring constant is the same irrespective of the masses attached to it. The spring constant is an inherent property. Well, we want TPQ over TP. Well, let's do that. TP is 2 pi times the square root of m over k. Well, if we want the ratio, we're just going to divide them by each other. And this is where even folks who had it correct at this point, every single one of them got it wrong because of the algebra. So let's walk through this together. The first part should be obvious to everyone that these 2 pi's will cancel. So that means we are left with TPQ to TP is the square root of 3m over k divided by the square root of m over k. Now you may think you know some shortcuts in your head, but most people try to take those and they got it wrong. We have square roots. We want to undo that. The simplest way to do that is to square both sides. Squaring both sides becomes TPQ squared over TP squared is then equal to 3m over k divided by m over k, which then is 3m over k times k over m. K's cancel, m's cancel. So we're left with TPQ squared to TP squared is 3. Well, we are looking for TPQ to TP, taking the square root of both sides. TPQ to TP then is the square root of 3. That is the ratio. And since square root of 3 we recognize is 1.732, about that. 1.732 is greater than 1, so that means the period is larger with PQ than it is for just P. And that is part A.